this. Actually, it might need to be. Stretch that far. Is there a famous movie? Or gets misquoted a lot? It goes, batches, we don't need no stinking batches. These gone, this is my batch. But he doesn't actually say that. He never actually says it in the movie, but it's very famous. It's very dark right here. Look at that. I think we're going to be okay. It hasn't turned on. This thing hasn't come on yet. Oh, look at that. That doesn't work out very well. So we got I forget this all the time. Well, we'll do our best here. First off, we'll do this and then come down further here. Because there's a little spiel I'd like to talk about. We're going to do some problems. We're going to work through some things. Let's see if we can record this stuff or some of that stuff to start with. Oh, this is going to be good. Oh, it's already recording. Oh, we've already got some of this. Oh, it's going to be awesome. It's because it looks like monumental. Because it looks like I'm standing away. You don't see it. Okay. So we're going to do some problems. I invented a problem the other day, and it was hard to do. It's got to practice the exam myself, and I time myself to see the thing. And I usually aim for like 9 minutes for my time, right? So if I do 4 problems, 9 minutes. 36 minutes, so then I double it for you, 72, but you have 75. It seems like a reasonable thing, so we're aiming for. When I was getting on minute 20 on this problem, I was like, yeah, this problem's too long. So I brought that problem too, in addition to the ones that are posted up on the blackboard. And I didn't bring black. I have all these other colors where the learning can take place. But let's talk a little bit about what could be on exam 1. So exam 1 this semester is different from the previous semesters. We used to have some particle Newton's second law in there. I said, hey, we should change the arrangement of the classes. So we broke classes 4 and 5. Class 4 used to be a path and polar coordinates. We decided to make it break it down into classes 4 and 5, and then make exam 1 just the first 5 classes, limiting it to particle kinematics, which is in chapter 11. In here, this is the book. It's called a book. You don't own the book. I think you're trying to just make it harder on yourself. You like a challenge. So I just won't say I won't buy the book. I'll have tens of thousands of dollars of an education, but I won't buy that book because I want to save some money. But anyway, read the book. This is chapter 11. Lots of good stuff inside that book. So here's our lists of stuff. Fundamental kinematics. That's those first 3, like 4 equations, I guess you could say. dv dt. Oh no, dr dt. dv dt. Yeah. Something like that. I'll look up. We'll see the equation sheet. I'm not sure how many people here. Oh, by the way, I'm going to do this. This is just for my records and for curiosity and someone's. So this will, you won't get any super prizes for this if you didn't show up here. You did, so I'm not telling you that. So please log in there. I just like to keep track of that kind of thing. How many people here from, let's see, Dr. Rico's class? Okay. Maybe even if you put it next to who's your professors next to your name? Yeah. Okay, thank you. Appreciate that. Thank you. How many people for Dr. Faraci, Professor Faraci? No, Faraci. So we got lots of people coming in though. How about Dr. Jasinski? Jasinski, okay, and Dr. Orloff. Okay, Dr. Faraci, or Professor Faraci, I don't have a PhD, usually does his exams differently, but the rest of us are kind of communicating with each other. We don't give identical things, but we're trying to coordinate a little bit more. Professor Faraci kind of has, he has this kind of like, these are his priorities, so he likes to give like less problems, but they're harder problems. So just to let you know, Some people get like a little anxious. He only had 2 problems, but they're harder problems. They're longer problems. Just, we try to balance the things out. So I know there's some. So for most of us, I think the rest are following in suit. I created an equation sheet, and that's a really important thing to get used to. Right? There's a lot of reasons for it. I don't need to maybe sell you on the reason why we have. I'll even go right here so the people who get recorded can see that I'm standing here instead of hearing my voice. They can see my coffee cup too. We decided to, or I decided to, use the equation sheet because when I have people make their own equation sheet. I usually have rules like you can't put problems on there, and you can't put like a recipe of a step-by-step thing. And people write really, really small, and a lot of times that's the last thing they'll do because they procrastinated and have all these other courses. So they'll waste all their time, exam prep time, making this equation sheet and writing itty bitty bitty, and then they're like in the wee hours and they didn't have time to practice solving a problem. So then they don't do well in the test. So I say, well, I'll just give them an equation sheet and bypass all that nonsense, and there you go. So that's the idea. But getting used to that equation sheet is a really important thing. So I would say, as you're preparing for the exam, print that thing out, and that follows with the drum I will beat for the rest of my career. Only way to prepare for an exam is to simulate the exam. Is to practice problems. Get a problem, don't look at the answer, work it all the way through. But I'm going to be here today to try to work some problems, kind of give you some hints and maybe advice on how to go about that. But the real way that you're going to be prepared for the exam and you're going to nail it, you're going to kill it, is practice a bunch of problems until you get to the point where you get a problem in front of you and you go through it and you go, yes, I got it. And then you look at the answer and say, yes. And then looking through each of these topics, it'd be good if you could try to like isolate or find, be able to master each of these topics and feel comfortable with it. And then you'll kill the exam, right? But if you try to half-ass it, well, you're already the good students, right? Because you all came to this thing because it shows you give a shit, right? So there you go. I just swear around today, right? It's fine. You wouldn't believe how much I could get worse. So I'll try to stop. Anyway, so we had fundamental kinematics. We'll look at the equations on the next slide here. Projectile motion. We didn't cover that enough. It's assumed that everybody could do that because of physics. You had it probably in high school physics. But there actually could be a lot harder than you think. And they're the kind of problem I like to ask because it's the first kinematics problem that existed in humankind. When we threw spears at some food, and said, they had to shoot higher than the thing. Why? Oh, okay. And all kinds of, sports, or all playing projectile motion. Projectile motion's everywhere, so we should be able to do any projectile motion problem. Like, oh God, but you can make them real hard. Constant acceleration, well, that's a special case of fundamental kinematics. Relative motion, this is an important thing for dynamics. Got to try to get that straightened out. Make sure you have triangles often, but also vectors. And constrained or dependent motion, we could often, we just pulley problems. Rectangular coordinates, coordinate transformation, and then path coordinates and polar coordinates, and being able to do these various things in these 3 coordinate systems, and then be able to jump in between them by a coordinate transformation. So those are the topics that are going to be covered. And with many things, it's really hard to read. But you have your own, right? So you could get this off of Blackboard, download it, print it out, feel good about it. Let's see what I was going to say. Okay. So up here in the blue corner, that's really the stuff that we're covering. Actually, I could probably have fixed this. This was from last year. So let me make it even. Let's make it seem less. All right, so it's going to be up to right there. Okay, that's so much better, right? So you don't have to do nearly as much stuff as last year. Boom. Okay. So that's the stuff on the equation sheet. These are the tools that you have available to you. And so you go, hey, V is equal to dr dt. That's what that says. Oh, yeah, it's over there. And acceleration could be dv dt, or obviously, it's the second derivative of position with respect to time, or the wild card, velocity times the derivative of velocity with respect to position. If we're going to implement those for a uniform velocity, we end up seeing that I just used x for no, it could be anything. It could be y, it could be z, it could be s, it could be q. I don't know. Nobody would use q. But the constant velocity setup right there. And then you could have uniform acceleration. So now we could have just v is equal to the original velocity plus acceleration times time. Or you could have the position one, where we have the position the final position is equal to the original position plus the original velocity times time plus 1/2 times the acceleration times time squared. Then the one that we always forget about because he came from the wild card is that velocity squared equals the original velocity squared plus 2 times acceleration times the change in position. And then we have relative motion, which seems relatively, that's funny, easy thing, but it's a very powerful equation for relative motion. And we can remember that there are actually vectors, and they can be made into triangles, and that can help us in a strategy to solve stuff, to use those triangles. And then last we have path coordinates, what's special about the velocity in path coordinates? Thinking about it. What is it? We see path coordinates and velocity. Or if I just say velocity, actually, this might be a good thing to always remember. I mean, just almost like a reflex, right? Say velocity, you have a reflex. And a reflex should be, it's always tangent to the path. Velocity, always tangent to the path. Right? The path coordinate says, it doesn't even need the normal unit vector. It's just the speed times the tangential unit vector. And then we have acceleration in path coordinates. Well, we have the change in speed, right? So the magnitude of the speed can increase or decrease. That's in the tangential direction. But now we got this crazy thing right here where we go v squared over rho in the normal. What's that guy's name? What do we usually call him? What's his name? It's good to have a name. Nickname too. How about centrifugal? Right? Or centrifugal? Centripetal. I don't know what the difference is right there. I said centrifugal. I never learned to pronounce anything anyway, so I'm an engineer. I don't need to. But yeah. So, and remembering those things, it kind of makes it a little bit more familiar, right? It kind of helps you, makes a little connection there faster you think of things. Then you got polar coordinates, which the book calls radial and transverse. That's a little more difficult. I use a cartoon in class to talk about this, but for velocity, we got r dot. That in my cartoon with my buddy Newt Dog, he's sitting on a stool that's spinning, right? And he's got a what do they call that? A fishing pole. There you go. I forgot that word. And the fishing line panning out. That's our r dot. That's the rate of the fishing line going out. And then we also have the r theta dot. And that's the end of with that line out right here. That's because of that r times the swivel chair, right? So we have those two components being able to break out. Same velocity, whether you have rectangular, path, or polar. They're all the same velocity. They're just expressed in different ways. And then when we did the acceleration, and you just had this you might even have had it just yesterday. But you have sort of like a convoluted thing that's got 4 terms, so it could be a little bit intimidating because of that. But if I maintain that same idea of this guy sitting on a spinny stool and with that fishing line going out, we can start to break down what those things are. R double dot, that's just the fishing line going faster and faster, spooling out. It's going woo, and it makes that noise. Woo, like that right there. And then r theta double dot is kind of interesting right there. That's actually centrifugal acceleration too. That's a little weird, right? But if you look at that negative, it's multiplied by that ER, that ER is pointing that direction, that negative means it's going that a ways, right? Right towards the center of where it's moving. That's just like that normal acceleration. So that's it. So now we're confused right here. What are the other terms? Okay, E theta. Well, that's the chair spinning faster, right? R theta double dot, right? Where we had R theta dot. That was the component because we're moving along here. We're going to follow that particle. That's actually really tangent to the path right here, but we're using polar. We'll explain why we need polar and path. Why would we need two things? And we seem to have a lot of overlap here. But now we got that R theta double dot. Well, the chair is starting to spin faster. Right? Before he was constant speed, but now we go. The chair can start going faster. And now we got this crazy other one right here. He's got a name too. Anybody remember him? Coriolis. Rhymes with aurora borealis. Is that right? No, it doesn't really rhyme. Kind of. Anyway, Coriolis, that's the mythological toilet bowl draining in one direction in the southern hemisphere versus the north. It's not true. But hurricanes do spin the other way. I thought somebody was asking the question. But it doesn't have to be me talking the whole time. You'd ask a question. I'll shut up now and do some examples for you. One last thing. The reason why to follow up the path and the polar. Why do we have two different things well, actually we have three. I'd rather stick with Cartesian, right? Descartes, he came up with that, right? With the Cartesian. Well, why do we have this path and this polar thing? Why would we care about that? Like, what's the difference between them? Why would we use the path instead of polar? Got a lot of the same stuff in it. Well, if you're following on the path, if you're going along for the ride, if you are the particle, if you're in the car, path is a way to go. But if you're polar, that'd be nice if you're like stationary in one spot and you're kind of tracking something like the radar. Right, that's a classic one. Where it'd be a lot easier to figure out all these terms. Like if you could figure out, oh look, this distance from me is this speed. Oh, and it's getting further and really quicker. Oh, and he's turning this way. You have when those are the things that you're measuring, polar becomes a really useful thing to try to go between. Right, so that's the motivation to have it. Right, that we can have these things, even though they're measuring the same stuff. All right, so here you go. Here's the evil problem, and let's see. What's the best way? I go back and forth when this way to do this. I think I'm going to put the problem up there and do the work down here. So if I had planned this a little better. Hurt your neck, right? It's like the first row in the movie theater. Oh, right there, that stupid board. I complained about this the other day. In this room. And he's going to hit the fire. Oh, I think I got it right there. Okay. So I found this one out of the book, and I thought, I like this problem. Okay, cool. This will be a good problem to ask. It's got multiple things going on, and a lot of professors like to do that. Then we don't have to ask as many problems, multiple topics. There's more topics. I wanted to ask 4 problems most of the time. I don't like 3 problems, because then one's got to be 35, and 30 points, right? Or 30, 30, and 40. Or I could just make one really big and the other small. But then you bomb that big one, and that just kills your grade, right? So I think that 4 problems is just about right in terms of okay, you don't do very well, but you got partial credit on that, and then you kick ass on the other 3, you're going, right? That's just my perspective. So we got train A, point A, is 1.6 kilometers from a crossing traveling at 130 kilometers per hour when it applies its brakes and slows down with a constant deceleration. Its decreased velocity is observed to be 96 kilometers per hour when it is 0.8 km from the crossing. Now another car and this is this is a jerk. At point B, moving at 80 kilometers per hour, no idea how fast that is, by the way. The metric system boggles my mind. In Canada, you see, like, speed limit, you go, woohoo, but then you get pulled over because you thought it was miles per hour. Is 2 kilometers from the crossing, which is a pretty long way off, but then somehow he spots the train and says, I'm going to beat the train. In an unwise effort to beat the train at the crossing, the driver steps on the gas and accelerates. The angle between the road and the train is 60 degrees. The car miraculously, I added that word in there because it was funny, beats the train to the crossing by 4 seconds. I originally made it closer, but I decided no 4 seconds. I was going to make it by 1 second. Find the relative velocity and relative acceleration of the train with respect to the car when the train passes through the intersection. Provide the magnitude and angle with respect to horizontal, indicating quadrant. And like I said, I didn't. When I looked at this, it seemed like I even peeked at what the solution was, and I said, "Oh, it seems like it's doable in the time." But then they like cheated in their solution right there, and they're always cheating in the solution sort of thing. So when I started to work it out, I actually had to go to migrate to a second page. All right. So how do we approach this? That's the big question. What do you do first?
Write down the node.
There you go. I like that. Everybody on board with that? All right, do that then. Write down the nodes. Like in any kind of organization that you want.
I was going to say draw a sketch.
Draw a sketch.
Tell me to draw a sketch.
Draw a sketch. That's good too, right there. Hey, that's just as equally of a valid thing. But here's the thing. Do something. No, this is really, really, really important. I see lots and lots of people, enough to break my heart, to turn in blank exams, not having written a thing on a problem, and that kills them. That's just evil. Please don't do that. So one of the reasons why, I know the reason why. I've been there. You just don't even know what, you're just like, just like panic hits, right? You don't know what the hell to do. Well, that's, interestingly enough, we can make an analogy. That's inertia, right? Problem-solving inertia. Got to get over that inertia. So the best way to do that is just start doing something. Start writing something down. Easiest thing, write down. So you're actually organizing your brain. It also, after you're practicing this way, also gets you into your routine, right? We want to get into that. It's like exercising, right? It's your warm-up kind of thing. This is my method of doing something. And I think everybody should try to do it. All right. So one thing for me, probably I would have given in parentheses next to everything here, I would have solved this right here. So because I believe given enough time and motivation, you could do the units conversion. So I don't need to actually test if you're able to convert units. So I probably would have put these in parentheses after I had decided, okay, I think this is a valid question to ask on an exam. So we got that out of the way. But if you're in another course that doesn't have a professor that's as nice as I am, that might be something that you want to do in your solution strategies.
Do you remember TA89?
I do allow it, even though I know it's the seat of policy, because I think they're delusional. Yeah. I even say that on camera. Is this even going to pick that up though? This is what I'm going to say. I can't quite tell. That's how old I am. Well, I can't see it because my big head gets in the way. I think it's picking it up. I don't know.
Did you guys say you can do unit conversions in the TA89? Yeah.
Please, if you're going to do that on an exam, write down that you did that. Yeah. Because numbers appearing for magic give professors this little itchy feeling that maybe they just, I got it from the guy sitting next to me.
You just click second 3, and it pulls up a bunch of categories like velocity, all these volume, mass, and then you just type in the numbers. So you would type in, say, 130, and you'd click under velocity, kilometers per hour. When you press enter, it'll give it to you in meters per second. It's just kind of helpful sometimes.
All right, so things that I know. at 1.6 kilometers, and I might turn it into meters like really quickly right there. So I might even, as I'm putting it down there, forget about this. That's me here, VA, and I might call that VAO is equal to, let's see, which one's that? That's the 130, right? So he's 36.11 meters per second. And then at 800 meters, VA is going to be, let's call that VA, we can even call that VA1, maybe, all right. Trying to organize our brains here. That goes to 96, right? So that's the 26.67. And then at 2,000 meters, right? This is VBO, BO, is the 22.22 meters per second. All right. What do we do next? Well, I'm not going to do that drawing. Maybe I want to do that sketch right there, right? So even though we have this, the thing above, maybe I'm writing on top of that, but I can't reach up that high. So we go to this right here, and this is the 1,600 meters, and then right here is the 800 meters, and then to right here is where B starts out. Here's my 2,000 meters, and then here's my 60 feet. Because I'm trying to think of the thing. Here's A and here's B. And I didn't take a lot of time to do that, but it kind of helped me to organize my brain, kind of see what's taking place here. And so what are we going to do first? What do you think we should do first now, after this point? What would you do?
Write down what we need to find.
Yeah, you could do that. Yeah, I mean, if you want to, we could write down what we need to find. So we're going to put it over here. Find. Right here, right? We want to have V, and how are we calling this? We're saying that's going to be V of the train with respect to the car, right? So that would be A with respect to B. And we also want the acceleration there. All right, so now what do we do? Stinking word problems.
Start by solving for one of them.
Well, yeah, but there's probably going to be a lot of stuff in between. So that's a really good thing to say. Okay, so here is, I've said to my class, said to you, here is the method by which that we go about solving engineering problems in general. Most of the time you don't know exactly the path that you're going to have to take from the beginning to the end of the problem solving journey. So you just have to kind of start someplace. A lot of times it's going to be experience, and as you become a more experienced engineer, it's hard to even explain to a young engineer how you knew to do something. But if you're there by yourself on the desert island without anybody to ask, and you need to solve something, the best way, or you're by yourself during an exam, is to just try something. Right, and because you've practiced from the exam practice problems, you're just going to try something out, or maybe try to look and try to gaze over the thing. And go, what can I figure out now that might be helpful to me? Look at the very first. Oh, go ahead. What's the very first thing that they tell us about? You can answer your thing. I was just giving the hint.
We seem to know more about the motion of the train than the car. We don't know the acceleration of the car, but we know the deceleration of the train.
You see that thought process? Yeah, you could do that. All right, so that's the thing we got to get better at, right? We got to pick it apart and kind of like read in between the lines, look for hints, right? So I think that's a good place to start. Can we get the deceleration of the train with what we're given? Yeah, we can. And how do we do that? You guys know, right? Yeah. We have this distance right here. We know the speed right here is 36.11 meters per second. The speed right here is 26.67 meters per second. Therefore, we could go, we don't need to know the time. We can go v squared, let's say a, and let's call this VA1. This is VA, and I put the parentheses there, and we could call this VA2 right here, what his is going to be. And so we can get VA1 is going to be VA0 squared plus 2AA times, let's say, just say delta, and I don't want to go X's and Y's right now, I'll just go delta SA. So from right here to here is 800 meters, right? And here, so we got 36.11 squared, nope, excuse me, 26.67 is that one squared, 36.11 squared plus 2AA and 800 meters. So we're able to find AA. It's going to be a negative value, right? Because it's decelerating. And let's see, where did I go? Where did you go? I get a negative 0.3704 meters per second squared. And I also, from this, I know its acceleration is 0.3704 I meters per second squared. I'm going to need that when I go to find this. Now, we had somebody else that said that the first thing we should do, right, Grace, right? We said we could maybe solve for, just try to solve for the thing. Well, what we could do now, or an alternative to what I just did, right? So maybe you didn't recognize this, but I could write down, okay, I have this in my, in my view when I'm doing the test. Maybe I'll write down, well, okay, I know that this is equal to V right here minus right here. Or I could have looked up the equation in the equation sheet, which was written in a different way, right? They had that over to the side over here, and then I'll write that down. I'm just doing something, right? The same thing over here. For the acceleration. I have that now. So if I started here, maybe that's to say, okay, here's the things I need. And, remember reading the problem, that we're going to say, as it passes through the intersection, when the train passes through the intersection. So this is a constant acceleration, so I know this thing is going to happen right here. And so I can work in that direction. That's going to be the thing, like, okay, which of these things can I figure out? That's the train of thought, no pun intended. That's the train of thought, because it's a train. That's why it's funny.
One thing I want to mention is like the importance of selecting your equations. So for instance, we use the v squared equals v naught squared plus 2a change in position. And what's really important is that you look at what you have. We have two velocities known, and we have a change in position known. We don't know time. And if you look at some of the other equations, they all have time. So what you need to do is find an equation where you know everything but one thing so you can solve for that one thing. So yeah, if you were to look at... Yeah, if you were to look at this equation, there's multiple things that you don't know and you might feel stuck. So you need to be able to look at your equations and look at what you have and figure out you need to use.
That's a really good point. A lot of times we go like, oh man, I don't know that, I don't know that. So this is like actually one of those instances like I described, it's a maze, right? Every engineering problem is like a maze. For all your other courses too, so the skills that you build up in dynamics are ones that transfer over into other courses and to your engineering career, because you don't know how to get to the end when you're starting. What you got to do is you got to start, and you go down a path. Here, we go down this path in the red equation up there. It didn't lead us anywhere. Okay, got to take a step back and see what else we can try, right? Now, you don't want to randomly do this for the rest of your life, so with experience, you get better at like trying to figure out, pick what path is going to be the best one or the likely one. But because you have insight when looking at the thing, you don't necessarily have to write that down, but you get triggered by looking and say, velocity, position, oh, that one. That's the one I want to use. It's a really good point. All right, so we made it. We've got some stuff down. So we got some partial credit. All right, so now I maybe I want to continue on this. So I have this. Maybe I want to get this guy, the velocity of A, at the intersection. So it's a constant acceleration. How do I go about, and this is one of the reasons why it was a harder problem than I expected. I just didn't recognize it when I was picking the problem out and glancing over what they did for the solution. And by the way, I do hit, my short attention span is so good for me to reset and like totally forget what I had seen before. It's like a brand new problem to me like 10 seconds later. I just totally forgot what I saw. But when I had glanced at the thing, they do this like with their calculator right here. So your TI-89 could be like a really like useful thing to this right here. When we get to this. But how do I figure out the velocity at the intersection, knowing what I know here? I swear there's got to be an easier way to do it.
Using the same equation you just used.
Yeah, that's a good one. By the way, I just misinterpreted what I had written there, but that's fine right there. So we could go and say that the velocity of A2 squared is going to be velocity of A, and we could either pick here or we could pick there, and so let's just do this one right here, plus 2 times, I'll write the equation up, delta S, and I guess I'll go 0 to 2 on that one. So we have VA2 squared is equal to our 36.11 squared plus 2 times our minus 0.3704 times our 1600. And I think if we do that, we will find our VA2, VA2. I did it a different way, but I bet we get 15.19 meters per second. I hope we do. And actually, by doing that, we're actually we found an easier way than the way that I had done it. So thank you. But sometimes there's multiple ways to get to the same place. So I just identified one. That probably saved us a lot of time by doing that right there. That's good thought process. So now I actually have that guy. So I have him and I have him. Now I have to ask myself, how do I get VB or AB out of this? Well, how about this? Okay, so it's a constant acceleration. And hopefully we said somehow that we say he accelerates. We really should have added that in there in the question. And so if you're not clear on that, if you think the acceleration changes with time of A, maybe you should ask the professor during the exam, say, hey, is the acceleration of A constant? And like, oh yeah, it implied that, or we should have said that. I think it should have said that. It doesn't say anywhere. Steps on the gas, it could be having, the acceleration could keep getting more and more, or it could be decreasing actually. You know, that usually would typically be the thing, right? You can't keep like zooming up your engine, it just won't let you, you know. So if acceleration wasn't constant, it would probably be kind of decreasing with time. But anyway, so what we can know, what other piece of information we've given is time, right?
The velocity of A2 we got is 10.89.
Where?
The velocity A2.
Really? Huh.
Yeah, it's funny.
It is funny. Let's see. I'm going to wonder why that is. What did I do onto here that would have been different? Well, let's just do it the best we can with that. All right. Well, I'll stick with that. What'd you say it was?
10.893.
Are you sure about it? I just want to make sure that I don't change all the numbers if you maybe made a little math error into the thing. Because I think I changed this thing so I did get the same approach that they did. See, double checking that because I have varied off of what my original solution was based on someone's response. They were saying, I think this is okay here. Yeah. Huh. All right. Well, anyway, what I can do. Okay. So the answer to what I was getting at is that we know something about time, right? Well, we know that when things we can find out what the when A crosses crosses this thing, right? We can find out when A crosses based on what we have right here. So we have that the velocity, let's see, A2 right here is going to be equal to the original velocity plus the acceleration of A times the time. So now we're able to find T is going to be, I'm actually questioning a whole bunch of things. That's okay. I think, I went the other direction for this thing. So in order to get this, I had to take the, maybe I'll show how I went about this. I should have vetted this out a little bit more. With these other numbers, right, when I had that guy right here at being 15, I got 68.09.
Same.
Was it the same? Okay. So something happened when I put up with that math right there. So the 68.09 was the correct number. So here's saying, okay, so we had to actually read the problem here a little bit more closely at the very end there. The car miraculously beats the train to the intersection by 4 seconds. So now we know what time A was at the intersection. So, or makes me B. So B at the intersection was 68.09 minus 4, or 64.09 seconds. And because of that, we're able to find what the acceleration of B is going to be. Because we could have like what delta, let's call SB, is going to be equal to, of course I brought that S0 over to the side because it's a delta. And I could say right here, the original times the time plus 1/2 acceleration of B times time squared. So I say that it's 22.22 times my 64.09 plus 1/2, yes, plus right there, E times 64.09 squared, and that's going to equal my 2,000. And if I do that, I end up with, okay, so I'm hoping this is the correct thing here. Yeah. AB is going to be equal to 0.2804 meters per second squared. And now I have this. All I have left to do is to find that velocity at B, and I'm pretty well set. So how do I find a velocity at B? Remember, if we're going to do a relative motion thing, a lot of times, right, we have to be careful that we're comparing the right thing. And we're totally okay with this acceleration because it's constant. But the velocity is changing. So we've got to make sure that when we're measuring the thing, that they're happening simultaneously, right? So we could find the velocity of B when the train, which is this guy right here, is crossing. So we could take and we could find, I think this camera thing is not going to work at all. I'm not even sure it's still recording. Yeah, it took us a long time to do this. Running out of space here. Might have to erase some. Let's erase something. So we can find the velocity of B at the moment that we care about. It's going to be T of B is equal to, that's going to be the 68.09 seconds. That's the time that we care about. So BBO plus acceleration of B times that time. I guess B, I don't know about putting a B in there. So we have 22.22 plus 0.2804 times my 68.09 seconds. And I say, hopefully, it ends up being 41.31 meters per second. And then I have that. So now the rest that we need to do is to solve this. Of course, I'm going to have wrong values based on here. Is to maybe to write these out right here. I could find the velocity of B. Of course, that's the speed of B. I want to take a look at this thing. He's probably going to be like over here somewhere. Traveling, it's right here somewhere. And the horizontal is going to be 41.31 times the cosine of 60 degrees I plus 41.31 times the sine of 60 degrees J. And I wrote that on the bottom of my thing, and it didn't print out on the bottom of the thing. I scanned this, and then I printed it. So I take A. I already had that written down somewhere, maybe. Velocity of A, we decided that was going to be 10.89 I meters per second. This is meters per second. So we could have the velocity of A with respect to B is just going to be whatever this was. Anybody want to give me the number?
I think the VB is to be 40.2, because it's now 68.9 seconds, it is 64.08. Should it be?
No,
No?
should be 68.09 because we want it when A is right here, right? We want to know the relative velocity between these two. This guy is 4 seconds beyond the intersection.
Oh.
It's happening at the same moment.
Oh, got it. So now, I see. Thank you.
You're welcome. Anybody want to give me numbers here, or we could just
20.66.
say again? What was that?
20.66.
20.66. Well, that makes sense because it's right, 1/2. How about this guy?
35.7.
Okay. So we want to say that it's going to be 10.89 minus 20.66 I plus, and then this is going to be 0 minus 35.78 J. So minus 35.78. And what do we have here? I can't do that in my head. It's going to be negative 9 point something, right? Bueller?
9.77.
9.77. You really ought to have another Siggy Figgy in there, just until the end. All right, and then we want to make sure that we are, this becomes second nature to us, that we've read the problem, what they require, you read that last line, provide the magnitude and angle with respect to horizontal indicating quadrant. Well, that's a real long way to say. Yeah, what I want to have as my answer needs to look like this right here, blah, 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 meters per second, and then blah, 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 and then say some angle right there. So what do we get for the magnitude right there? Taking the square, some of the squares.
37.09.
So we can answer 37.1. And we get theta is equal to, and I like to not play a game. You have to be careful to play with the negatives because negative and negative can cancel out. So you basically don't bother with the try to use the numbers, just reason the thing through. So go rise over run. So it's always going to be the y 35.78 over the 9.77. So what's our angle? There.
74.7 degrees.
So we have 74.7. And we want to answer with the correct quadrant, which is going to be that guy right there. Because both of these are negative, so it's going downwards right there. So that's like the completed part of this other velocity of that thing. I told you it was a long problem. But what's a really good idea to do is like, oh, wow, that doesn't really kind of make sense to me. I always draw the triangle just to double check because that could have messed up the thing. I'm kind of like, does that make any sense? The way I like to write out when I'm doing a relative velocity problem, I'll say the velocity of one of them, let's say, is going to be A. Let's see, no, wait a minute. So I said A with respect to B. Yes, okay, so I have the velocity of B plus the velocity of A with respect to B. That's the thing I just solved, right? Yeah. And when we're saying this equation right here, we're saying we're using B as the reference. Right? And when we're going to do a triangle for this thing, we're adding these two together. So we have the velocity of B is going in that direction, right here. And I should have drawn it upwards that way. Let's see if I did the thing right. Yeah, and the velocity of B is coming up like this right here. It's much larger. So maybe I want to exaggerate that. So I'm going to actually have the velocity of A with respect to B is going to be like this right here. So here's the velocity of A. Here's the velocity of B. So I could look at that and I could go, okay, I buy that thing is going to be going down this way. So if you have like a little ruler, you know, especially I have this really nice one that I like that's got like clear, and it's got on one side it's millimeters and on the other side it's inches, but in tenths of inches. So it's really quick. It's really easy to pick. Okay, one is larger than, you know, those increments. So you can just use, you know, whichever one to have a proportional thing, kind of get the angles just about right, and so you can confirm what your answer is by doing the triangles. You can also do this by triangles right here, which is not too terribly difficult to do, but it might take, some people prefer to do it, but this will definitely help you on an exam if you could do it quickly because you've practiced doing it, right? To double check yourself so you know that you nailed it. And basically, once you do that, you know that you got off the right. The most that you could lose is probably like a couple simple mistakes that you might have made, and you just didn't end up with the right answer, which that usually doesn't count for much, for missing many points. And then the acceleration is the same thing that we do for here for the relative acceleration. And asking both of them, I saw as I went along, I even crossed that out. I said, as I was going to think, okay, we're not going to ask it because it was taking too long in the middle of the thing. And then I said, well, then I got to the end and I said, I think I even turned somebody came by and asked a question, so I didn't even bother figuring out how long it took. That's a really long problem though, right? Yeah, it took us like an hour to do. Also, I had the blah blah. I had to tell you about the Happy Days thing, which was really important. Does anybody have any questions on this? You could totally do this, right? Given enough time.
Yeah.
Yeah, but that would be the big problem on the thing. So I'm not asking this problem because I just. We can do some more problems here. Now, once again, for my class, I'm going to turn on the solutions to all of these guys right here. So here is you can't read that. Let's put this down here for a second. Oh, it's coming down. Let's see how fast I can erase it. Oh, it's coming. It's coming. Seriously. The exciting part. We're making it virtual. I didn't do it. Okay. What was that? Was it Indiana Jones fan? I created this problem at the Coast Guard Academy, the Angry Birds thing. Actually, I don't know. It might have been. I think I made one as a preliminary one. We never used it. Because that looks like one of my colleagues. That was her thing. I would have been much more exact with my arrows. Yeah, I know. Pompous ass. The Angry Birds, though, decided, so this is a projectile motion. Somebody asked me this last year and said, why don't you just use that VO thing right there? And that's the answer, by the way, that I'm providing you with the answer. It was a kind of an interest. I was puzzled by that suggestion. Why don't you just plug that in? That's what we're asking for. That's the end. But so there's a projectile motion problem. I want to save that for you to use as practice. There's another projectile motion. I definitely did that because I'm a big Michael Jordan fan. So try here. That's also pretty much the same problem, right? You get the original velocity. Here's another projectile motion problem. Now we want to find out this distance right here. Okay, determine the distance at which the pilot should release the water so that it will hit the fire at B. Right, so another projectile motion. Here's fundamental kinematics. How do I know that's fundamental kinematic problem?
Because it says it.
Yeah, okay, that's excellent right here, but it didn't in the original one. Yeah. Let's say because the acceleration is a function of time. Maybe that's the thing that just jumps out at me, right? Or the acceleration is a function of something. So now I'm going to do some integration, right, with my different accelerations. dVdt or VDS or whatever it happens to be right here. But this is probably going to be a more straightforward one because it's a function of time. It's those ones that when acceleration is a function of position or it's a function of velocity, they get a little bit wonky sometimes. Here we go. Here is one of this. Once again, this is a function of time. You look at acceleration. You can put it, acceleration is a function of time. So they kind of tells you. If they didn't put that t next to the thing, you can still see there's t inside the sign. Sometimes you could turn this thing around a little bit. You could ask the question or ask for a particular thing where you need to go. The order in which you solve the problem could be reversed from when there's an A and a B. So always be on the lookout for that. Don't get stuck thinking I got to solve A first, right? It's a trap. A lot of times I've been, lately I've been not asking A's and B's as much as asking just for the end product that you would need. And you need to go through multiple things to get there, right? So that's like, I don't know if it's fair. I think sometimes I think it's telegraphing too much when I do ask you an A and you solve that, and then you can get B. I just told you the steps to get to the thing. And then you could cruelly all of a sudden turn it around where you actually have to do B first. Here you go right here. So this is a fundamental kinematics and a polar coordinates combined right here. But now that theta is a function of time and r is a function of time. So remember for anything that's dealing with polar coordinates, we really want to do what I call the variables of interest. And I think I didn't highlight this in class. But I call them the VOIs. They don't go VOIs, they go V-O-I. I like to make O as part of an acronym anytime I can. So when I go to do that, that's a lot of times when there's polar coordinates, it's either something I know or something I'm trying to find, or something I need to find as a mid-step. So any of those three things. So they are going to be R dot, R double dot, theta, theta dot, and theta double dot. And straightforward ones, you would just take the derivative of the functions like this one right here, just so that you could get these. I think I remember writing this problem, and what I wanted you to get was part C. Do you think you could do that right from the very beginning, the very first step? Do you think you have to do that the last step?
No.
Why is that?
Because tangent to the...
Yeah, velocity's over tangent to the path. Yeah, with a knee-jerk response, right? So you could just draw it as tangent to the path. Well, hopefully that you knew that it was going that direction. I don't know. You might have to play it to see the thing with the signs were at the end to say, is it going that way or is it going this way? Because you don't quite know. But you see at the t seconds right there. So you kind of. But given the dot, unless some maniac wrote this and that dot wasn't exactly the correct actual spot for this curve. But that is actually what the curve looks like if you were going to write it in X and Y on the diagram there. Interesting. Here you go. Here's another one. I think somebody I didn't write this one. Someone was copying me for the next year. Because we always divvied up who wrote what problem. And this one's a little too easy because it was either up or it's down, depending on the thing. But that one's way too similar, I think. Here's another polar coordinates one right here. And this is I believe this is a constant. Yeah, it's got a constant acceleration problem. All right, so this is not one that we're going to do. All right, so hopefully I didn't leave this one in there because this is actually a kinetics problem. Okay, here's a relevant. So if you have, maybe I should go back and fix that. I accidentally stuck a kinetics problem into the thing. It would really bother people a whole lot, wouldn't they? So don't do this problem. This is Newton's second law, in polar coordinates, I think, in path coordinates. But it does say that at the top, so there you go. That's it. Let's see, relative motion. And here's relative motion. Oh, yeah, that's a good one. We should try that one. Another relative motion. There's constrained motion. And people hate the pulley problems. So, okay, so what do you want to work on? Or do you want to do a homework problem? Anybody speaks up there when we get to the side. Be a leader. And I also put a bunch of these are ones that where I didn't provide the solution for. So maybe you're interested in doing one of these. I'll do this. Projectile motion ones. I tried to come up with like this was something that wasn't originally intended to be for students. I was trying to have a discussion with the professor. I was like, well, how many different versions are there? And this isn't all the different variations that you could have of a projectile motion problem, but it was just the ones that I found in another book that I was going to, okay, well, you could go, you can ask for this, you can ask for this, you can ask for this, you can arrange it this way, you can revert it back way. So that's, and I made this, and then like one of the professors said, well, you ought to share it. I said, okay, I will. Why not? I slapped the answers onto there, but I didn't write out the solutions to it. So what do you want to do? Anything? Polar?
No, pulley.
Oh, pulley problem. Okay.
Yeah.
Good pulley problem. All right, you got two to choose from. We go this guy, this guy. Yeah. I'm sorry. I meant to. I wasn't sure how we were going to do this thing. I was listening. Thanks, Pat.
Bye.
So we got this guy or this guy. What do you want to do?
That one.
That one? Okay.
We have a corner, so it's like 4 to 5 blocks.
4 to 5 blocks. Let me think here. Can I do? I could try one. I could try different. Let me hide this from you for a second. If I go to that's the right word. It's working, it's thinking. I go to my OneDrive and documents, and I'm writing a book, or it's almost done. So it's called the Engineering Dynamics Course Companion. And just so you know, I'm never going to assign it as a textbook. I think that would be well. But let's see, pulley problems. I think it'd be class 3. Come on. I'm trying to open the thing up. Can I just go like this and go download? Why are you so slow? Now let's see if we get up. Okay. So I'll show you. I think it's still the thing's warming up. I asked for a bunch of my fellow faculty there to help me review my book. It's due the 15th to be published. And they haven't gotten it. Like, Asai just really, he just blew me up. He told me like that back in November. I said, hey, can you look this over for me? No, I said, I need people to look it over. He goes, I'll look it over. I'm like, really? He goes, yeah, if you'd let me do it over the break. So I extended it. It was supposed to be due in November, but because he asked. And then and he didn't look at it. He didn't do his homework. So there's my dude. There's Newt Dog right there. He's doing the what do you call it? The right hand rule. There you go. we go projectile motion. What was this? Was this dependent? Did dependent motion go in here? No, I got the wrong one. No, I got this. This is a relative motion. So is it class 2? That's been class 2. Right, it's not opening, it's inside. Oh, it did eventually. Class 2. What do we do? Delete. No, I don't want to delete. Jesus Christ, let's go show. Download. You know how many hours I spend on this thing? Crazy. Dependent motion. That's the one I did in class, isn't it?
Yes.
Yeah.
Yes.
Yeah, that's real good.
Yes, class.
You did this one in class?
Yes.
Okay, so I just wasted our time. Yeah. So some of this book is stuff we already did. Damn it. Okay, sorry about that. Yeah, I don't have any off the top of my head. Actually, now that I'm in here, I could go and find boom, into here, to OneDrive, and go to Documents, and go to Books, Dynamics, Peter Johnson. I'm afraid to do this live. It's chapter 11, all problems as PDFs. That's all the problems. Let's see. So you want to do a complicated problem? Can you find one in the book that you want to do? It's a bunch of blocks. It's not that many problems in the book. We do problem 1156 maybe. Do a problem 1156. Or we could do problem 1159 maybe. That's the hardest one, right? Or 1160 is even harder. System starts at rest, the change of position of D. Okay. So that would be problem 1160. That's 11160. Let's see. Alright, so I haven't done work through this thing, so we're going live. I need the calculator help all the way. Oh man, we should turn this later.
Yes, one of either of those.
That's better. Look at that. Alright. Is it still recording? Yeah, I don't think it's going to be good. Alright, so here's the problem. The system shown starts from rest, and the length of the upper chord is adjusted so that A, B, and C are initially at the same level. Okay, that's not fair. A, B, and C are initially at the same level. Each component moves with a constant acceleration. well, that makes sense because they're all tied together. They would have to be. And after 2 seconds, the relative change in position of block C with respect to A is 280 meters upward. Okay, so you got to be careful here. Relative position of C with respect to A is upward. Okay, so C is higher than A. Knowing that when the relative velocity of B with respect to A is 80 millimeters downwards, the displacement of A and B are 160 millimeters downwards and 320 downward respectively. Well, they're really trying to screw with you, aren't you? The acceleration of A and B, if AB is greater than 10 millimeters per second squared. Determine the acceleration of A and B if the change in position of block D when the velocity of B, velocity of C is 2. That's crazy. All right, so all kinds of damn things going on here. I might want to actually even draw this. Well, let's start with the right place to start. We'll say that this is going to be, I like to use X's, you don't have to use X's. But one of the very first things you're going to do is start drawing datum for this. So this is going to be XB, and this is XC, and over here, all the way down, XD. So we have how many cables here? Two. Yeah, so we have 2 equations. So we'll start out with the first one, the L1. Is marching through here. We're going to have 2 times XA, right? Just follow right here and right here. And then we're going to have this guy right here. That's going to be XB. That's just going to be XB right here, right? So it's going to be 2 times XB. This is supposed to be this is the last problem in the chapter, so in that section, so it should be the hardest one, right? And then you're just going to have XC. This seems pretty easy. Except the hard part is like all the words that they have up there. So then we could just look at this and say, oh, okay, it's going to be 2VA plus 2VB plus VC and 2AA. I'll call this now as 2 times AB plus AC. And then we go L2. That's just going to be this distance right here, so it's going to be XD minus XA. Then we're going to add that to this guy right here. That's going to be XD minus XB, which turns out to be 2XD minus XA minus XB. And then, of course, you could just say 2VD minus VA minus VB. And 2AD minus AA minus AB. So, okay, so we got done with a lot of stuff that was kind of easy, or kind of the heart of the things. Now the rest is like this constant acceleration type of nonsense here. So we want to see each component moves at a constant acceleration. After 2 seconds, the relative change in position. Okay, so here's one thing that you should know. Even though we have this equation up here that's a constant, if we go down to this guy right here, right, we could say that all of these are delta dx dt, right, or delta x delta t. Right? And then we can just multiply it by the same delta t. So we can also say, even though this one is a constant up here, we can also say that it equals 2 times delta xa. Not enough room. Making a mess. I'll put it down below this. I'll write it over there. 0 equals 2 delta XA plus 2 times delta XB plus delta XC. And the same thing down here is 2 times delta XD minus delta XA minus delta XB. Right? So one of the first things that they tell us
here is that after that's 2 seconds, the change in position of C with respect to B. So we can say delta x C with respect to A is going to be equal to 280. I'll stay in millimeters, even though I don't like it. And we'll go upwards. Got to be careful here. Remember that all these guys are downwards is positive according to this right here. We'll just be careful with that. Basically, though, everything's fine because they're all going to be relative to each other. It's mostly when it's like x's and y's that you have problems when you're on 2 different planes where you have to worry about not being too devoted to the sign conventions. Okay, so we also know that that means that's going to be delta xc minus delta xa is true, right? Anytime we say that c with respect to a is the same thing as saying that one minus that one. And knowing that when the relative velocity, okay, so this is at t is equal to 2 seconds. That's an important thing. Now, at some other time, probably, knowing that when the relative velocity of color B, which is downward, okay, so we have V of B with respect to A is going to be equal to 80 millimeters per second downwards. The displacements of A, when that happens, displacements of A and B are, okay, they told us delta A first. And they said respectively 160 down and 320 down. Determine, right? So here's our find. Accelerations of A and B. If, I don't quite understand how that's going to play into things right here, what they mean by that. They didn't say what they meant, whether it was down, upwards or downwards of that B. That's a little weird question. The change in position of D when we also want to find B. Change in position of block D. So we're going to find delta X D when VC is 600 millimeters per second upwards. Okay. Well, I'm taking a big risk by doing this. All right. Okay. Well, what I would do next is try to manipulate and see how I can put this guy into practice right here. So can I use that to find something out about this right there? I think so. I could, because I have, is that 2 seconds right there? All right, so I know that piece of information. So I could say that anybody have any suggestions on this too? Not putting me on the spot to try to do this. You have, and I'm not above like looking at the solution. I'm trying to do these things. It doesn't say anything about A right here. So what I can do is I can replace I don't know if I want to replace C or I want to replace A as part of this. I'll try to replace C because nothing asks about C right here. So I'll say delta XC is going to be equal to 280, and I'll leave off. I'll just assume I won't write the thing any more of the. I don't want to be any more of the units onto it. Right. So now I can take that, and I have eliminated C over here. I can write that into its place. So I wish I had written smaller. I can get rid of that. Lots of things. Why did I just get rid of that? I just need to get rid of that. I didn't mean to. Get rid of something I can remember here. All right, so 0 equals 2 delta XA plus 2 times delta XB plus 280, right? 280 plus delta XA. So now I got another delta XA right here. But I have one equation. We also know that happens at 2 seconds. So that might be something that's going to help us. We could, one thing we could actually say when we have something along those lines is we can actually, we could actually use the constant accelerations things into play right there with the. Well, we know it's okay. So I'm just thinking out loud here. So I'm sorry about that. So we could use that the x is equal to x naught, or let's just say delta x. The delta x is going to be the original velocity, right? Which is all 0, they're all starting at rest. So let's just not even write that down. Right? But that would be times t plus 1/2 a t squared. Right? So because of this right here, that might be the secret to to using this. Because now what we could find is we could say that the delta, we could say this 280 is equal to 1/2 the acceleration of c with respect to a times our 2 seconds squared. So now we have another piece of information here. We can find c with respect to a, the acceleration there. The dentist is telling me I have to go next week. Great, thank you. So 280 times 2 equals, and then divided by 4. So we had 140 millimeters per second squared. And I believe it's still going to be upwards right there. So that might be something that we can use. We might even know, let's see. All right, well, this is greater than. Okay. I want to try to use. I think I've gone as far as I can on that. Now let me use this piece of information right here. I got 80 when that happens. Right here. Okay, so I don't want to worry about this value is not true right here, but this relationship is right in there. Right, that they have. Wait, let me double check here. No, this right here might only be true. Yeah, that's only true at a given time. Damn. Okay. I gotta be careful with that. I gotta be careful that that's only true at right here. We have this also right here. We can also find out what the velocity is at this time, or the relative velocity of the thing, because it's starting at rest right here. So we can, and so we know the amount of time onto the thing. So we could say the velocity of C with respect to A at that 2 seconds right there is going to be equal to the acceleration of C with respect to A times the time right there. So we're going to say that it's 140 times our 2 seconds, or it's going to be equal to 280. And because it's going upwards with the acceleration, that must be true right there too. So we have that information. And how can we get, now that we have that, well, the acceleration, this is always going to be true. This is only true at that 2 seconds. So it's the acceleration one that I think is going to be the most useful thing to me out of all of this. So remember that that means that we could write, just in the same way we've written up here, the acceleration of C is going to be 140 plus the acceleration of A. So that one's always true. So that would probably be better to like put back into this guy right in here. So we said it equals 2AA plus, well, we can actually just jump to this right here. We just did the math right here. AB plus 200, and nope, 140 plus 140. So I don't think I needed to use that right there. But this guy is something right here. So we've reduced that out of the way. And that's always true. Okay, so here's the next thing. This is how we do it. Do you see what just happened to me? Right, as I'm going through this. This is a demonstration of what you have to do. Right? This is a harder problem to do during an exam. But I'm telling you, this is the process. I don't know how to do this problem. I haven't seen it before. But I just figured it out. Does that make sense? What I'm trying to explain? Right? That it's not something that you're not capable of doing. It's just something that you got to get better at doing. And the only way you can get better at doing it is practice. Right there. That you suddenly, the light bulb just went off in my head. Like you can even see, oh, we get a little excited about it, right? Then it's like, okay, I see what I got to do now. All right, because this right here, A and B have this relationship. I have another relationship between A and B. So I'll be able to make 2 equations and 2 unknowns, and then get everything I need to know. Does that make sense? Did you see the thought process that was going through, or did it just look like randomness was taking place? I went down paths that didn't work out. But, okay, I mean, during an exam, that kills you because of the amount of time that it takes to do that. But you get better and faster at doing it. And we always try to make exams that are doable in the time, right? There could be mistakes that happen when we accidentally put the thing out. But by me taking the exam, we try to solve the thing. All right, so this is our golden ticket right here to be able to do part A. Part B is all going to be about, part A doesn't care about D. So let me just to get rid of some of this maybe. And I already wrote down what I needed for this, I believe. I don't think I need this velocity anymore. Of the C. I don't think I need this guy anymore. So, yeah. Okay, I'll move that out of the way. All right, so here's what I have to say. I can say the velocity of B with respect to A is 80 millimeters per second. Let's call it downwards negative right there. So I'll say that that's negative. Well, I don't know. This is X and B. We know that that's going to be velocity of B with respect to A. Velocity of B minus velocity of A, right? And Oh, we also know that the delta x of, let's say, b with respect to a is going to be delta xb. I get tired of doing this time. XA. Right here. So we could say, let's keep it negative too. So it's going to be negative 320 minus 160, minus 160. So that's just minus 160, right? I'm doing it in my head, so don't trust me. Is that true?
Yeah.
All right. So we know here we have position, a change in position, and we have velocity. So can I get the acceleration from that? Can I get the relative acceleration from that? I could say v squared is equal to v squared naught plus 2a delta s, whatever, right? So now it starts from rest. So I can say VA with respect to B squared is equal to 2A, but I said A with respect to B with respect to A, B with respect to A, and then delta X, B with respect to A. So I could say that that's going to be negative 80 squared, so the squared didn't matter, is equal to 2 times A, B with respect to A, and then I said that it's going to be negative 160 right here. So I can say that A, B with respect to A is going to be equal to whatever 80 squared is. Could probably do this in my head if I was smart. So divided by 2 and divided by 160 equals 20, right? So I got, it should be negative 20. So now I know the acceleration of B with respect to A is equal to negative 20, but that's equal to the acceleration of B minus the acceleration of A. So the acceleration, let's say the acceleration of B is going to be acceleration of A minus 20. So I can plug that into here. Did I do that right? Yeah. So I can say equals 3 times the acceleration of A plus 2 times acceleration of A minus 20, and then plus 140. So I get the acceleration of A. So that should be, we're going to have 5A, so 140 minus 20, but it's going to be minus, right? Minus over here, divided by 5. So 140 minus 20 equals, divided by 5 equals, so I'm going to have negative 24 millimeters per second squared. So that's, I said at some point that negative was downwards. All right. So, and the thing was asking for the accelerations of A and B. If the acceleration of B is greater than 10 millimeters per second squared. That's a really weird thing to say. Right? But we could say that the acceleration of B now, going back up over to here, is just going to be negative 24 minus 20, or minus 44. Now, are they saying downwards is positive or downwards is negative? Let's see what the solution is after this. What's that? It'd be funny, yeah. Embarrassing to me, but funny to you. Would that be right? Is that how that works? Thanks.
Yes.
I put myself out there, you know? Okay. Cry out loud. All right, let's see. Let's check it out. But here's I'm trying to demonstrate the way to approach problems isn't necessarily perfection here. Because that was so let's see, Beer Johnson. What about the individual solutions? I don't want to look at the individual solutions. Let's go. I was looking at the 12th.
Oh, the past. Right.
It's this one right?
Maybe.
What are you doing? Just go, get larger. Let's search. Son of a bitch.
Whoa.
Okay, 150. All right, so it did the same thing as me. And well, we got, it's going to be hard to read. Okay, so there's a, these are, okay, so we made, then I wrote down the notes. Here, just up and this down. They made it all wise. Did this, got that 280, got AC equals AA minus 140. They shoved them in here. And we got the velocity. And I got 40 here. I got the 20, right? And they got a 40. Why did I get pay no attention here? I got negative 24. Wonder why. Let's take a look though at the process. They had t equals 4 seconds. Where the hell did 4 seconds go? They must have solved for the time when it happens.
Yeah.
Okay. So 320 equals this right here. So they say when it happens, knowing that when the relative velocity of air is going to be displaced with air being downwards to 320, it's better to determine knowing that when. Right. So I guess, yeah, we could have figured out the time, but I'm wondering why we did that. Okay. Huh. Anyway, this was the process. I'm not telling you that it was like a perfect one. It was a more difficult thing. So I'll have to go back and try to figure out what I did wrong. B with respect to there is that acceleration T. Oh, did I mess up over here? That's the thing that I think I could have avoided using the time by doing this right here, right? So they found the time, but I did it with position. So there's a way that I could have been doing this incorrectly. I found that velocity, right here, and I know when that happened, that these two things were true. Did I write something down there? I think my way has to, no, I do have that as true in there. B with respect to A, they do the same thing. They get that same thing somewhere along the line. Yeah, the velocity of A with respect to B is 80, and then they do this and they solve for time. Yeah, but they never actually write out the acceleration of A with respect to B. They write this thing right here with time. We should have got the same answer. Yeah, I have to sit down and like puzzle it out and see what I did wrong. But yeah, I'll write the thing up and post it onto I don't know. I guess I'll have to send it out to the other instructors to be able to put it onto their blackboards. But I'll put that one up there. Anybody want to go through another problem? Some other problem?
Homework problem.
Okay. Which homework problems?
Just start with the first one.
Do one.
Homework 1?
Homework 5.
Homework 5, problem 1?
One, yeah.
Isn't that due?
Tuesday, yeah.
You want me to do your homework?
Not exactly.
Okay.
What we say. Yeah.
You say it that way. I guess I can go to blackboard. Why does he keep doing this to me? I hate you. Where's blackboard, damn it? It used to be the first thing they would apply for teaching about blackboard.
Okay.
Human resources development. What the hell? Let's go to blackboard.
Blackboard.hartford.edu.
Okay, but I usually this is the way that I like
Or
it.
you just
Black-
go to hartford.edu.
Or dot
Hartford.
Hartford.
Ooh, that's kind of like a urban. Ooh. Very fast.
Yes. I'm Kenneth Long.
All right, so how would you go about? Oh, whoa, look at that. We can talk our way through this. I don't like solving homework problems as part of the help room session because I really don't want to take that away from you.
Okay, the three go very similar.
What did I say about polar coordinates? One of the first things you want to do, or was that?
You mean start the idea of how it started?
Yeah, that's what,
Yeah,
that's
not
what I'm
doing
trying to do.
everything because I want to by myself too.
Yeah, I want to do it actually.
Yeah,
What did I say when I wrote down something over there on the side? Do you remember
Oh, the I.
the VOIs?
UIM.
Variables of interest. Yeah.
Yeah.
So try to get those. Right. R dot. You get R dot, right?
I just don't know, like, when I read the question, which is which.
Which
Like what's theta, what's theta dot. That's hard.
okay.
Like that.
Um,
Where to start from?
where to start? Well, when you want theta dot, how do you get theta dot from what they give
And
us?
then just like the derivative of the main
With respect to time.
time. Okay.
Yeah. So that would be
So like we have
pi times 2 pi times the cosine of pi t, right? Theta dot.
the derivative.
Yeah. Taking the derivative of theta, which is 2 over pi sine of pi t. And we can find at time t, we can just plug that in there. And you got to remember though that for many things you don't want to use your angles as degrees. You want them as in radians. So make sure you're switching your calculator over to radians when you're getting something like that. Most everybody. Well, anytime. Well, for any time that you see something like pi or something like that inside the sine of the cosine. And for lots and lots of problems. And actually, the only time you don't use radians is when someone gave you degrees. right? Otherwise, just assume that it's going to be radians. If it's involved in some kind of numerical thing that's going on. Unless it's a geometry thing that's in degrees, always assume it's going to be radians. So we could find theta dot right there, right? Just by taking 1.25 after you've taken, it comes out to be 2 times the cosine of pi t, right? So 1.25 times pi, take the cosine of that in radians, times 2. But then if you want theta double dot, you just take the derivative of that other one, right? So you take the time derivative of theta dot, which is going to be 2 times the cosine of pi t. So the derivative of cosine is a negative sign, though, right? So now you're going to get negative 2 pi times the sine of pi t. Is that true? I think so. And then you put 1.25 inside there, and I have theta double dot. Then you go down and you look, and we're in R dot. So you go, what? You can distribute 6 through there, and you're going to take the derivative of it. So that first part, that 12, is going to go away. So you got, and then anytime you take the E, right, that just takes the negative 1.5 down. So it's going to be 6 times 2 times negative 1.5 times E to the negative 1.52. So that's R dot. So I can't do that in my head. What is 12 times 1.5? 18? Is that true? So negative 18 times E to the negative 1.5 t. I can't do an E with negative. And then take R double dot. Yes?
Can you, so as part of this question, like I did parts A and C because they didn't require any like transformation with the angle yet.
Yep.
Could you possibly just go over like the angle transformation?
Sure, absolutely.
Like the setup? To get to
I'll do it without another time. So I think it's still recording.
I just think it's the solar
Stupid things in the way. That's a problem. All right, so when we come up to this thing and we get, we can find what the position is going to be, right? So we could find what theta and r are going to be at a particular at a particular time, right? By just sticking from the original problem where they gave us theta. We can take in 1.25 and stick it in there. We get what theta and r are equal to. So that's going to tell us what the position vector is going to be in terms of, it's not, I don't know if I want to say that. It can tell us where the coordinates are of the thing, right? What the orientation of that point. If we need that. I don't think we do, but that was my first thought. So we want the velocity of point A in rectangular coordinates in I and J. So that's going to be our ER and our E theta as part of that. So remember that that's going to be theta. So that's our coordinate system. That's how our coordinate system is arranged. And we're given a velocity. So if that's true, as we're looking at the thing, right? I don't know which quadrant it's going to be in. It depends on what the theta is going to be, right? When you put the 1.25. So find what that theta is. Of course, it's going to be given to you in radians. You got to put it into degrees here to be able to find the thing. So it all depends on what theta is equal to. So let me see if I can do this with my calculator. I can actually find what the numbers. Actually, I don't know if I can turn this into radians. I don't think I know how. Let's check it out. Okay, so if we go 1.25 times pi is equal to 3.2699 pi. So if you divide by pi, you get 1.25. But you multiply by 180, so you get 225 degrees. So that's going to be in the lower left-hand quadrant, right? For 225 degrees is going to be down here. So if you subtracted 180, it ends up being 45 degrees. So that's really which way our ER is facing. I hope I'm correct in this, by the way.
I think I did that wrong in conversion to degrees. I got 25.79. So
Probably calculated.
okay.
You round off the pi. I don't know. I think it's true, right? It's just me 1.25 times 80. 180. Well, actually, to tell you the truth, I just did that wrong. I'm sorry. I just did that wrong. Never mind. Take that back. What I just said. I didn't do that on purpose. By the way, just my brain jumped. Forget about that. I did that wrong. You need to stick in 40. Let's see. I guess let me stick in 225 and take the sine of that. What is the sine of that? Is a negative 707. Yeah. All right. So I took the sine of that, and that's supposed to be times 2 equals, and then divided by pi equals. All right. So that's negative 45. Negative 0.45015. So that's going to be in radians, right? I messed up by putting the thing in there. So what I'm trying to say is that I went into here and I went sine of pi and then 1.25 right here. If I do that, I get a negative 4.45015, but that is in radians.
Is it 2 over pi?
Was that?
Isn't it 2 over pi? Yeah, it's 2 over pi. It's 2 over pi.
Okay, I thought I did that, right? I said that pi times 1.25 equals, right? I just did this, the same thing we just had a problem again. I want to convert that into degrees because my calculator doesn't do radians. So, dummy me, I just did it again. We divide by pi and multiply by 180, and so we have 225 degrees. So I want to take the sine of 225 degrees, and I end up getting negative 0.707. I multiply that by pi, or I multiply that by 2, and then I divide by pi. And so what I get is a negative 0.4502 radians. But I want to know what that is in degrees because I don't want to do my coordinate transformation in there, right? So if I multiply, I got to multiply that by 180 and divide it by pi. So I get a negative 25.79 degrees. So now I know that I'm in this quadrant right here, and I have my ER right there, and so I have my E theta right here, and so that right there is where that theta was. And now I could do a coordinate transformation thing either way I want to go. I go ER and E theta right here, and then I go I and a J. And so now, once I set that up, I can turn my velocities into that. You had a question?
Yeah. How did you know? I'm
still not sure how you converted from radians to degrees.
Okay.
How you got negative. How the whole angle thing confused me.
Right, so this guy right here is going to be the same, you know, like pi is equal to 180 degrees.
Okay.
So if I want to leave this in degrees, I can take the sine of 1.25 times 180, which comes out to 225 degrees.
Okay.
I take the sine of 225 degrees, I multiply it by pi, I divide by, what, did I just say that again? Yeah, you were telling me this before and I wasn't listening. Right? So this is that answer right there. I just wrote it down now. Right? So I have this right here now. This is the answer to that equation.
Okay.
But I don't like radians.
Right.
My brain don't work in radians. So once again, I took my multiply by 180 and divide by pi
Okay.
to be able to get from here to here.
Okay.
I'm sorry, I skipped that step. All right. And now we have a negative 20 right here. And now we know that that's going to be our coordinate system. So we're able to take this and J, and the ER is going to be, so that's going to be the cosine right here, and this always messes me up. So the ER is going to be a negative sine. So wait, I did it wrong. For the J, negative sine, or sine. Then for the E theta is going to be positive sine. And then hopefully it's going to be a cosine. So now, when we got in part A, we got the velocity and polar coordinates. So we could just apply this and get them into rectangular coordinates.
Ted, the E theta, is that a negative sign?
There should be no,
Or is that a smudge?
no, just a smudge.
Okay.
Sorry. Yeah, you should always look for only one of them is going to be negative, or only one of them is going to be positive.
Well,
And,
E
they'll be-
theta's in, I'd say E theta's in the first quadrant, which I know are both positive.
Yeah.
And the fourth quadrant is negative Y, negative J, and positive I. So
Yeah, I didn't think of
it's
that.
kind of a check.
Does that get you on the right track on it?
I think when I had set up my thing, I had E theta and E on the wrong place, so that kind of was backwards.
Yeah. Is there any other problems anybody want to go over? I don't want to do the rest of the homework there for you.
One thing remind Ted?
No.
One thing that you mentioned in the moving coordinate systems, like ER and E theta and the path coordinate systems, they are not necessarily orthogonal. They're not right-hand coordinate systems. The ER and the E theta can be oriented in any direction you like, as long as you start out. If you start out a particular orientation, as long as you're consistent, it should work. For I and J, no, you have to leave it fixed as they are.
Yeah, the path can be backwards. Although I say it's still a right-hand coordinate system, except that you're just looking from the other side.
That is so weird because the normal direction's always flipping.
Yeah, it could be. It could be in any but I still say it's a right hand because then it's just that the Z changes what direction it's going to be in for the thing. You just flip this thing. I want the world to be organized. Just want my right hand.
Right-handed.
So, because it really messed me up when the instructor for electrical engineering decided that the truth is it's actually a left-hand rule instead of a right-hand rule for the direction that inductance goes, because we actually have polarity inversed from which one is actually which way electrons move from ground. They don't go towards ground; they come from ground. Apparently, someone found out, but who gives our ass? The rest of the world did this way, but he insisted we do everything left-hand rule. And I think it was because he was left-handed. I don't know.
Can you go over one of the problems from the homework that we already got back?
Sure.
Okay. I'm pretty sure it was from class 4. It was the one where B's on A, they're moving relative to each other.
Well, I haven't posted a solution yet, have I?
Yeah, that's why I didn't know what it was.
Okay, I usually wait till I give it back, maybe, but everybody should have already turned it in.
Yeah,
right?
you did get it back to us.
I gave you 4 back? No, I haven't given you 4 back.
Oh,
No, maybe I did.
No, yeah, we just got homework 5, so we've gotten 4 back.
Oh, wait, was it 3? Yeah, it was 3. It's homework 3.
Okay, cool.
Even if the solution's posted, can you just like walk?
Of course, absolutely. I was going to. I was only mentioning that I was looking here on Blackboard and I saw, oh no, it's not posted yet. I was feeling all shame. Okay, so which problem were we at?
There's number 3.
All right, so yeah, the real important thing that we do as part of the start is to get our datum set for this. And in this case, we have one here that we're. Oh, I get so angry at Adobe. Yeah. They want me to update their thing all the time. It's all about them. All right, so walk through this right here. So we set up this datum right here, and we say we have to recognize that this is A, B with respect to A. It's kind of because it's a moving, because this whole thing is moving. So that's the only. This is the only thing it can be because this thing is sliding, right? But this is by a stationary datum, so we can go ahead and say A is moving along in this point. So we can, when getting the length of the chord, it's going to be 2xa time plus 1xb right here. We're okay with that? I mean, it's a little, I'll grant you, it's a little kind of like you're jumping to a something that not necessarily, how was I supposed to know that? You know, the answer to that is, well, you had to think your way through it. If you didn't know, if you got completely stuck, you could send an email and I'll give you a hint which way you're going. All right, so once we have these, and we were told something along those like the velocity of B with respect to A, right? But that was part of the givens. No, at the instant shown, velocity A has a velocity of 9 meters per second. Yeah. Okay. So and velocity and the acceleration is 3. So what we're able to do is we're able to say, all right, well, we solve for one of these two right here. I would say 2 times this is given, so we know what the velocity of B with respect to A is going to be, and the same thing down here. We're able to get the acceleration of A with respect to B. So the way I've shown it here is I said, well, given that I know those things, I can work through either with triangles or with components. And it's right here where I can enter in the things that I know to find the velocity of B. Up above, I have the velocity of B with respect to A. I know that has to be at like the 40 degrees going downwards, right? And I know the velocity of A has to be at, I guess I have it right up here, has to be 25 degrees downwards. So I'm able to get the I and the J for A, and I'm also able to get the I and the J for B. So now, B with respect to A, so now I'm able to get what the velocity of B is going to be. Does that make sense? Yeah. It's a lot easier to do it in the components. Yeah. When you get to over here, what you have to do, you need to write out and remember, maybe I don't hammer this home as much this semester. I usually do, about my way of doing the vector triangle is they always go nose, nose, tail, or what, I should say, if I'm going to, on the part where I'm going to add to this right here, I go nose to tail, right? Let me see if I do this the right way. VA is this guy right here, and VB with A is going this way. So that nose goes to that tail, right? And so now when I want to get this solution, this goes tail, tail, nose, nose, right to there. And we know that this one's going to be the 25, and we know that this has to be the 15 right here. And I also didn't need to point out that we think our way through, because I did the absolute value thing up there as opposed to playing with the sign conventions. For me, I don't feel comfortable with those sign conventions of treating them positive and negative and going here. You could do it, but the datum now is telling me we will find out that it's negative, right? So one is going down and one's going up. So I guess the sign conventions would help us out. In any case, that we know that this one has to be going up if that whole thing is coming down just by observation of it. And so now we can go for and if you've already found it out this way, that's fine. But still, you get this answer here, and I'm like, I'm not quite sure that makes sense to me. This triangle will definitely help you out as a backup to try to convince yourself. So even if you don't use the triangles and the angles and so forth to get there, I really highly suggest that you practice and drawing them out and having a ruler that has that makes it easy to do that. So that's one reason why I like that one particular ruler, because it's broken down into tenths of inches as opposed to having to do quarters and eighths and stuff. Is that clear?
Yeah.
Does it make it?
I like overthought it a lot.
Okay. Well, that is like a real big pitfall in working through the problems. There's I wouldn't say that's a confidence thing sometimes, but it is like a little bit of like, I think overthinking sometimes you can have a little bit of like, man, it must be more complicated than I can understand, right? So maybe a little bit of that. I tried a problem I didn't know how to do out of the book. It didn't go well. Yeah.
Oh, you got half the problem, right?
I got half the problem. I got most of the way through, and I do believe that I think I'm right and they're wrong. That's the kind of arrogance that will get you in trouble. I definitely have like an oscillating thing between like overconfidence and then like humility. Right? Like I get overly humbled by like, it seems like it's been my whole life. Like you think you should be like you get balancing out right here, but then there's an overcorrection.
It's an
It's an unstable control system, really. It's, overcorrecting. Like, oh yeah, I'm brilliant. I'm a moron. Here I come, dummy. Yeah, okay.
in there.
I think I've stabilized. Another question? Calculate. You want me to do the numbers?
No, it's okay.
That's a messy one. That takes a lot of visualization.
Yeah.
That one.
And it still bothered me that they came out to be the same angles, but I guess they're tied to each other, so they gotta kind of. But I wanted it to them to actually be different from each other. But I guess they kind of have to be the same angles. I guess is there an instance where they wouldn't be? I don't know. And they're tied to each other, literally.
Yeah, but they're moving at two different angles, and I think that really changes things.
Can we do the Angry Birds problem and just do the projectile motion?
Sure, absolutely.
Unless someone wants a different projectile motion problem, but I like that one.
Okay, Angry Birds. Is that gonna be too small? I should have just stuck to the script. Oh well. Even in playing in a band, I like to improvise. It get boring if I say okay, so Angry Birds decide that their next move will to be hit. What? These words are wrong.
Hit where the star is.
Will be to hit where the star is. Okay. If the bird launches with an angle of 30 degrees, what initial velocity should he, it's presumptive, launch with to hit his mark? Launch with to hit his mark. There's a lot of prepositions that are just turning up there. So the main equations that we want to go to are going to be and I like to go OX T. And then y is going to be YO plus VO y t minus 1/2 g t squared. In this kind of problem, it also helps to write out what these things are going to do right here. And if they happen to be down, negative, or whatever, I'll make sure we account for that. And it's good to decide what it's going to be we consider 0. So let's pick down here by the bottom, right here at the bottom of the cliff. We could pick right here where the launch is and then just make everything negative from there. Or have the delta y be negative. We can see that it's actually going to land down below him. Either way, we want to make sure that we keep it consistent. So we can list out the variables that we know. That the x at the end is going to be 20 feet. And the y at the end is going to be 8 feet. And similarly, XO, I might have done this one first, but that's all right. And then YO is going to be 10 feet. Is that true? Mm-hmm. 10 feet. Okay. And we don't know the time when this happens. There's the kind of information. We also have that theta is equal to 30 degrees. So I like always doing this because then I can get rid of that. So I could solve for my time. So it's going to be x divided by v o x, and then I can place my time. Here, and here. So I say that y is equal to yo plus, and then I also take care of these guys too at the same time. Put them into here, and say that we have our VO sine of theta. So that was this guy right here, times time, which we said right here, that ends up being x. But VO right here, VO cosine. We can jump ahead and say, oh, look at that. That goes there, and know that that's actually the tangent right there. Continuing on, 1/2 g, and now we have to have t squared. So that's going to be x squared over, you got to be careful, okay, when we put this guy in there. I probably would have been better to do in between steps right there to make sure it's not confusing. We have seen this one before. VO squared cosine squared of theta. So some people like to manipulate this and put it into, keep it as variables as long as possible. I kind of like at some point to start putting numbers into the thing. So we could say that the y was going to be 8 10 plus our tangent of 30 times our x was 20 minus our 1/2. Careful, 32.2 because we're dealing with feet. And then have our, what's it, 20, right? VO squared cosine squared of 30 degrees. And we can solve for a VO.
Remember from algebra 2, those are called parametric equations. Because you've actually got 3 variables, x, y, and t. But since t is not a significant part of the problem, we always say when a variable annoys you, solve for it, and then you get rid of it. Plug it into another one, and that goes away. So now we've eliminated t from the process because we really don't have any interest.
I was thinking that in terms of Excel. It's like if I want to plot a circle, it could be really annoying, right? Because I have to do it in X and Y. So what I could do is I could make a column of the sines and the cosines of the thing. And then I could go a column of angle, right? And so I'm actually plotting versus angle, from 0 to 360, but over to the right-hand side, I just go cosine and then sine, right? Then I have x's and y's, and I can plot x versus y. So theta is over there as a column, but you never see it in my plot. But now I can draw a circle in Excel because of that. So a theta in that case becomes that. Yeah.
And the other thing you talk about too is the VOX and VOY being VO cosine theta. That I call a constraint equation.
Yeah.
Because what it does is it eliminates 2 variables and puts them in terms of one of the other variables. Otherwise you would have had 5 variables, you wouldn't know what to do with it.
The most evil projectile motion problems are when you ask for theta, I think.
The launch angle.
The launch angle is evil. Because if you don't know the launch angle, you have to leave it in place, right? So let's say you know the initial velocity right here. So you're going through this equation right here. We say y is equal to yo plus tangent of theta x minus 1/2 g x squared over VO squared cosine squared of theta. And let's say you know the initial launch angle, initial launch velocity, and you know where it lands, right? So you have yo, x, and x squared, and theta is the one that you don't know. And now it's like, how do you get that? How do you get the algebraically? Did you go about getting that out?
Yeah, because you end up with a transcendental equation, and you got to use your calculator for that.
Well, what you could do is you could do this by hand. Because what you could say, you might happen to know that 1 over the cosine squared of theta is actually, let's see, I'm going to say this wrong. Is it the secant?
Oh, trigonometric substitutions.
Which is equal to 1 plus the tangent, it happens to be the tangent squared right here.
1 plus tangent.
Right? So that right there, so that ends up turning it into y0 plus the tangent theta of x minus 1/2 g x squared over VO squared times 1 plus tangent squared.
Now you have a quadratic.
Now you have a quadratic equation.
In tan theta.
So if you just go z is equal to tangent in there, and then you do the quadratic equation, solving for z, you get 2 answers. Right? Now you just take the inverse tangent of that z for each one, and the thing is that when you try to, let's see, here's the thing, you're zooming through here onto the thing. There's actually 2 paths that you could go by to get to with the same velocity that you can land into the basket. One is taking this one right here, taking the rainbow. But I think it's kind of interesting.
So the max Y is the only difference.
And I say this is the reason why I'm terrible at basketball. It's an excuse. I'm thinking about this, you know.
Yeah, I would think from a practical standpoint, the thing that you're most likely not to know is the log angle. When you're trying to figure out how to hit something from a certain place.